So what is the deal with finite elements and how can we explain them simply? So the idea behind finite elements is it's a mathematical technique, firstly, and it's a technique used to convert a partial differential equation into a system of ordinary differential equations. And the reason we do that is we find these easy to solve, especially by computer, which can solve them readily. So if we take the case of a bar, x direction, we know that at this end we'll call it x equals 0. The bar has length L, and we'll look at vibrations in the axial direction. So u, which is in general a function of x and t, since this is a continuous system, and also in general some load would be applied F, which is also a function of x and t. And in a previous video we showed that this gives rise to the wave equation, which can be written as u double dot, where that's the time derivative, second derivative with respect to time. This is a function of x and t, is equal to c squared times u comma xx, where I've used comma xx to denote the second derivative with respect to x. And this is called the wave equation, and c is equal to, or c squared, I can just say is equal to E over rho. Wave equation. We'll call that equation 1. Okay? And the idea is we would like to discretize this wave equation and convert it into an ordinary differential equation in the form of m u double dot of t plus k times u of t, where u are the nodal displacements, and that is equal to some function f of t. Oops. Yeah, actually, I'll do the vector sign there, and we'll call that equation 2. So we'd like to convert something that's on the form of equation 1 into something that looks like equation 2. Okay? And the way we do that is we use something called a finite element. Now you might recall that to solve equation 1, we use separation of variables, where we said that x could be written in the form of a function, that u could be written in the form of a function of x times a function of time. We found that that function of x turned out to be a combination of sines and cosines. Anyway, so the idea is if we go back to this drawing, we would like to solve this by finding approximate solutions, and I'll get to that in a second, what I mean by approximate solution. But the idea is we'd like to convert this bar into an element which has two nodes, node 1 and 2, we'll call them. And instead of knowing the displacement all the way along the length from 0 to L, we're saying we would just like to know the displacements at node 1 and 2, and we're going to approximate the distribution along the length of the bar. Okay? So at node 1 we're going to have, and I'll give it a generalized coordinate q1. That in general is a function of time, and there's going to be some load applied to the node, some nodal load, q1. And similarly at node 2 we have generalized coordinate q2, which is a function of time, and we have a generalized force, capital Q2, which is a function of time. Okay, and we'll say that this is a bar, let's just write this in here, which is continuous. And we'd like to convert it into an element which is discrete. Discrete in the sense that we're only tracking the displacement at two nodes. Instead of at an infinite number of points along it, we're going to track it at two nodes. So how does all this work? Well, the way it works is we assume, like we've done previously for the continuous solution, assume that the displacement field u of xt needs to satisfy the two boundary conditions of the element. So the two boundary conditions of the element, well, I'll write that in a second. Let me just finish this. So this would be A0 plus A1 of x, A1 times x. And because they're two boundary conditions, I've used a linear combination, and I've said that they're two unknowns, because I can solve two unknowns for two boundary conditions. We'll call that equation 3. Okay? And the boundary conditions are as follows. At x equals 0, u of 0 comma t is simply equal to q1 of t, actually. If we substitute 3 into 4, that gives us that A0 is equal to q1. Okay, boundary condition 2 says that at x equals 0, at x equals L, u of L comma t is equal to q2 of t. Okay. This implies that you can solve for A1, and A1 is equal to q2 of t minus q1 of t divided by L. Equation 6. Okay. Therefore, I can write from equation 3, I can write u of x and t is equal to q1 plus q2 minus q1 divided by L times x. So what did I do? I assumed a linear displacement field such that I could satisfy two boundary conditions, and by doing that I can solve for constants A0 and A1. I then applied the first boundary condition at x equals 0. I said that u is equal to the displacement q1. Since we know that, we've said it's q1. And then similarly, at x equals L, I said that u is equal to q2, and we know that because we've specified it. And based on that, we were able to solve for A0 and A1. We then substitute that back into equation 3, and we end up with this equation down here. Okay? So we found a displacement field. I can rewrite that displacement field as follows. Just algebra. 1 minus x over L times q1 plus x over L times q2. Call that 8. I can further rewrite it in matrix form like this. 1 minus x over L times q1 q2. That equation 9. And I could rewrite that in general terms as, so I want to write this phi transpose of x times q of t. And call that equation 10. Okay, so let me recap what I've done, make a little bit more space here. What I did is I took this displacement field, which I calculated as described above. I then rewrote it. Instead of collecting coefficients of x, like I had done here, I instead collected coefficients of q. And then I said, whatever the coefficients of q are, we're going to call shape functions phi. And to be clear, we've got this vector phi. Just write this. Got a vector phi, and that is equal to phi1 of x, phi2 of x, which is equal to 1 minus x over L and x over L. So what have we done? We've rewritten x in terms of shape functions multiplied by nodal coordinates. Maybe I should write that in just to make the point. This is a vector, the transpose of a vector of shape functions. And this is a vector of nodal coordinates. Okay, and the shape functions, if you look at them, really satisfy the requirement that they're 1 at their own node and 0 at other nodes. So if I look at this shape function, phi1, at x equals 0, it's 1, and at x equals L, it's 0. And similarly with phi2, at x equals 0, that is 0, and at x equals 1, at x equals L, it's equal to 1. And it turns out that these shape functions are not the exact correct functions, because we know from the exact solution that this should actually be sine and cosine. But as long as the shape functions are admissible, which means, and there's a rigorous mathematical definition for this, but admissible basically means it adheres to all boundary conditions, then any shape function that does that is suitable. I've shown you here how to derive one in particular, a linear one. But there are PhD papers written on this, and there are books on shape functions, and some shape functions are better than others. But the reason this is an approximate solution is because we're using non-exact distributions, shape functions. All right. Here's the spoiler, by the way. It's actually pretty accurate, and that's why we do it. But let's continue. All right. Let me also do a bit of math here, because I've got the foresight that we're going to need this. So I'm going to say from equation 10, let me just do a bit of math. We've written, and I'm going to drop the x and t dependency just for shorthand. We've written that phi transpose times q. Okay. The time derivative of this, u dot, would be equal to phi transpose times q dot, since phi is only dependent on x and q is the time dependent part. If I wanted to square that, and by the way, that's the velocity. If I wanted to square the velocity, I'd write that as follows. Q dot transpose times phi transpose times q dot. We'll call that number 11, 12, 13, we'll call this number 14. And similarly, since that's the velocity, we can look at the strain, which is u comma x, du dx. And that would be equal to, now the derivative is on the phi, because it's on the x-dependent part. It's transpose times q. And u comma x squared would be, this is just a bit of vector math, matrix algebra. It shouldn't haunt you. I'm going to do an example, and it will clear this all up. All right. We'll call that 15. I'm just writing it here because we'll need that on the next page. So just bear in mind that when I write it and say we derived it before, this is where it came from. That as a result of equation 10, okay, the expression for u, when we take the time derivative here, we take only the time derivative on the q, which is the time-dependent part. When we take the x derivative, we take it on the phi, which is the x-dependent part. And when we square something, that's just a standard way of squaring two matrices. Okay, and that's beyond the scope of this video to explain why that is. All right, let's go to the next page. So now the idea is how do we get these mass and stiffness matrices and corresponding force vectors? Okay, we've assumed a displacement field. We've discretized it, so we've taken a shape function and just our nodal coordinates. And now the idea is, how do we get a consistent mass and stiffness matrix so that we can get rid of all the x-dependent stuff? And for that, we go to energy principles, much the same way as we did for Lagrange's equations, and also in the case of Hamilton's principle. We look first at the kinetic energy. And we remember that for an n degree of freedom system, the kinetic energy can be written as 1/2 times q dot transpose times, I'm going to change color for this, the mass matrix times q dot. We'll call that number 1. And if we assume that the density and the cross-sectional area are constant, we can write the kinetic energy for a bar as 1/2 rho a times the integral from 0, times the integral from 0 to L, so 1/2 mv squared. So v squared would be u dot squared of xt dx. I called this 1, but of course this is not 1, it's 16. This is equation 17. Okay. Now if we substitute equation 14, which is from the previous page, that little bit of algebra that I did, into 17, we find that T can be rewritten as follows. 1/2 times q dot, I'm going to take the time-dependent part outside of the integral, times, let's change color here again, rho a times the integral from 0 to L, correct, phi times phi transpose dx. The phis are obviously functions of x, and the q's are functions of time only. Let's change color again for that. And I've done that so when you compare equations 18 and 16, you see that the blue parts are the same. So those must be equal. So your mass matrix can be written as, it's equal to rho a times the integral from 0 to L of phi times phi transpose. Remember phi, I'll write it here and then just delete it, is just equal to phi 1 of x, phi 2 of x. And phi transpose are just these shape functions side by side instead of stacked in a vector. So I just don't want that to cause any confusion. But that all that phi is and phi transpose, that's what it is. I'll make it clear in the next line. ds. Okay. And again, if we now substitute this in, let me write it one more time, as m is equal to rho a times the integral from 0 to L of phi 1 squared phi1, phi2, phi1, phi2, phi2 squared dx. Okay. We know from the previous page what phi1 and phi2 are, right? Phi1 is just, phi1 is just 1 minus x over L, and phi2 is just x over L. So we can substitute that in and we can integrate. That's the idea here. Okay. And when I do that, I find an expression, or I find a mass matrix that looks like this. M is equal to rho times A times L divided by 6 times 2, 1, 1, 2. That's the mass matrix. We'll call this 19. We'll call that 20. All right, let me split the screen in half here, and then I can do the strain energy and the K matrix side by side. So in totally analogous fashion, we proceed to find the K matrix by looking at the strain energy for the element. Yeah, and we call the strain energy U. Strain energy is the integral, by definition, of over the volume of the stress versus the strain. Stress times the strain, I should say, dV. And in the case of a bar, it can be shown to be 1/2 the integral from 0 to L of E A U comma x squared. That's a function of x and t dx. Okay? And if E and A are constant, this implies U can be rewritten as follows. It's equal to 1/2 EA times the integral from 0 to L of U comma x squared, that's of x and t, dx. If I now substitute 15, I believe it is, we'll call that 21, into 21, we get the following expression for U. U is equal to 1/2 Q transpose times, we'll change color again, E A times the integral from 0 to L phi comma x times phi comma x transpose dx, change color, times Q of t. Okay, so because the derivative on U here is now not with respect to time, but with respect to x, we take the derivative on phi, which is a function of x, and not the derivative of q, which is a function of time only. If that makes sense. So compare this definition with equation 18, where there's no derivative of phi. In the case of the stiffness matrix, this is how it's written. So let me rewrite it, and it will make sense after the next line. In the case of an n-degree of freedom system, we can write the strain energy as 1/2 Q transpose times your K matrix times Q. Okay. Therefore, we get this expression for the stiffness matrix. The stiffness matrix is equal to EA times the integral from 0 to L of phi comma x times phi comma x transpose dx. Substituting that in, it looks like EA times the integral from 0 to L. Let's write small. Of, actually put it in here, 2 over L. You know, I'm not going to do that. Just in the interest of saving some time here, I'm going to just put in the answers. You take the derivatives of the shape functions and then plug them in here and integrate them. And what you end up with is the following. Let's say K equals E A over L. 1 minus 1 minus 1, 1. Okay, so just to recap what we did on the page, using energy equivalents for the kinetic energy and the strain energy, we said, what is the energy of the system? And we put in the assumed discrete coordinates, the phi times the nodal coordinates. And when we plugged that in, we recognized that we could get an expression for the mass and stiffness matrix. These are called consistent. Let me write that in here. This is the consistent consistent mass matrix. And this is the consistent stiffness matrix. And it's called consistent because they're equivalent in terms of the energy that they store. If you take the bar and subject it to the same end displacements and velocities, the bar will store the same amount of kinetic and strain energy as if you subjected the element to those same displacements and velocities. That's what's meant by consistent. Okay, so finally what we need to do is account for the distributed load, and we need to convert that into nodal forces. Again, consistent nodal forces. And for that we turn to the principle of virtual work. So we look at virtual work. Okay, and for that we say that the virtual work, del W, is equal to the integral from 0 to L of the distributed load, f of xt, times the virtual displacement, del U, which is a function of x and t, dx. I realize I haven't numbered some equations. Let me just go back here and put 22, 23, and this one will be 24. Okay, and then we take the assumed displacement field from equation 10, where we've discretized the displacement, and we find that this can be rewritten as the integral from 0 to L, f of xt again, times the shape function phi of x, transpose, times del q. Del q is a function of t dx. Okay. Now obviously we can take the del q outside since it's a function of time only and rewrite this integral 0 to L of f. I'm going to drop the x and t just for shorthand now, times phi transpose times dx times del q. Okay. We would like to be able to write it in discrete form as the nodal forces q, the nodal force vector q transpose times del u. Del q, excuse me. Node is a vector. Okay. Therefore, it can be said that the vector q must be equal to, let's see, I want to write it, integral of 0 to L f of x t times phi, whoops, dot, times phi of x dx. Well, instead of phi of x, let me just write that out like this. Phi 1 of x, phi 2 of x. So separating it, I can then say that q1 of t is equal to the integral from 0 to L of f of xt times phi 1 of x dx. And similarly, q2 of t equals the integral from 0 to L f of xt times phi 2 of x dx. We'll call this 25. We'll call this 26. And I'm happy to say that we are done. Split the screen in two. Let me just recap what we've done. Equations of motion for the elements. Write that for elements. Can now be written in the form m q double dots. That's a function of t plus k matrix times q. So the function of t is equal to your generalized force vector. It's also a function of t. Call that 27. Okay. The mass matrix is given on the previous page. The stiffness matrix is given on the previous page. Q is given by equations 25 and 26. So we now have an ordinary differential equation where we've taken the x dependency part of the continuous bar and we've lumped it into these mass and stiffness matrices, and we've lumped the force, the distributed load, into a nodal force or nodal forces. Okay? So let me just write this all out. We can now solve this ordinary differential equation using standard techniques, whereby the partial differential equation we had before that, namely the wave equation, is very difficult to solve, and especially when the geometries or when the problems, the system, gets more tricky. So we converted, let me write this down, we converted the partial differential equation, the PDE, to a system of ODEs, ordinary differential equations, shown in 27 above. And we did this by assuming a spatial distribution. Instead of using the exact solution for the spatial distribution, we assumed it by picking an admissible shape function. So you write that we used admissible shape functions with phi I of x. And by admissible we mean, or we showed that it meant that the shape function should be 1 at its own node and 0 at all other nodes. Okay? And by assuming that, we were able to write the displacement u of x of t as something that was x-dependent multiplying something that was time-dependent, namely the modal coordinates and your shape functions. We multiplied. This could also be rewritten as phi 1 of x times q1 of t plus phi 2 of x times q2 of t. Okay? And then finally, we used energy principles to find the stiffness and mass matrices and the force vector. So M, K, and Q. And instead of a bar, we now have an element that looks like this. Q1 with force, Q1 applied there, and nodal coordinate Q2 and force Q2. This looks like this. Okay. And that's it for this video. As far as using this for some sort of practical problem solving, we'll save that till the next video. But I just want you to get the hang of what we did here is we discretized the displacement field, and we used energy principles. We used strain energy and kinetic energy and the principle of virtual work to find consistent mass, stiffness, and force vectors. I hope you found something useful out of this video. If you have, please go ahead and give it a thumbs up so that others can get to watch it. Thanks for watching, and we'll catch up with you in the next video. Bye-bye.